So we're going to write down extended Hamilton's principle again. There'll be one more term in it this time. So T1, T2, del T minus U plus variation of W plus the sum over K constraints dt. So just like before, except now we have this plus del W. That's called the virtual work. It's called the virtual work. And we need that so that we can introduce external body forces. We'll see that in a little while. I'm sorry, external forces, right? Boundary conditions, essentially, into the formulation. Sometimes if you have like a quasi-statics problem, the application of Hamilton's principle will be called the principle of virtual work, right? Because, if you don't have the acceleration terms, if you have acceleration then you have to really should be like principle of virtual power, right? Because you have a time dependence there, work per second. Okay, so the first thing we're going to do, so again, if I wrote out all the terms and put them into that equation and we started computing variations, it would fill up. It's going to fill up pages anyway. But if I try to do it all in one, it would just be too much to deal with, right? So what we're going to do is we're going to take the variations of those terms individually, kind of like we did before. So we're going to compute the variation of t, the variation of u. We'll write down what the virtual work is, and we'll compute the variation of the constraints. Okay? So we'll do them individually. And then we'll just collect all the terms like we did before. Okay? So first thing we're going to do is we're going to write down our constraint equations for this problem. There's going to be two constraint equations. One is going to be that for all species, the mass must be conserved. So we're going to introduce a Lagrange multiplier, and there'll be one for every species. So lambda alpha, and just to be clear, this thing is defined in the reference configuration, and we multiply by j alpha minus all right. So basically what this says in words, right? Remember what Hamilton's principle says in words is that among the admissible motions of the body, the true motion is the one that follows that equation, right? Well, basically, you'd say that equation is subject to the constraints, right? And one of the constraints that we're going to have on the motion is that mass of each species is conserved. Seems like a reasonable constraint, right? And again, this is over the reference configuration. So let's go ahead and compute del C1. It's equal to the sum over alpha, integral that thing, right? So again, just and I'm not, I think I mentioned this last time, I'm not going to write down what the variation of lambda is because it just returns the constraint equation, okay? So I'm just going to write the variations of the other terms. And what I'm doing is I'm treating rho bar, the local density, the porosity, or I mean the volume fraction, phi bar, phi alpha, and x alpha, or just x, as independent fields, okay? So basically, as of right now, my field equations are, as of right now, I need to solve for an unknown displacement, x, or position in the current configuration, the volume fraction, and the density. Right? So when I compute those variations, I have to compute variations with respect to all of those things, right? So let's look at what del J alpha is. So del J alpha is equal to partial J alpha, partial F alpha, and now I'm going to switch to additional notation. So Fij del Fij alpha. Right? Remember, our del operator is commutative with the differential operator, and we can use the chain rule and other things like that, right? So start there. Okay, that is equal to del J alpha partial Fij alpha so it's equal to that. Now, notice for the del xi, remember xi is the position vector in the current configuration, and all species are located at that point. But remember what these del are. They're variations of the motion, right? So while they all end up in the same place, there is an arbitrary variation on the motion of how they got there. So this is a variation of the motion, right? So in other words, if we go back to our drawing, the variation of the motion is this guy. Right? So this is del x alpha. Right? So that's why there's an alpha on the del x, but it's not an alpha on x, right? So at the end point, they end up in the same place, but how they got there, we vary, right? I think we already looked at this. Does anybody remember what partial J, partial Fi is? Partial F? Right? Basically, that's the partial derivative of the determinant of F with respect to F. And I think if you look back in your notes, we wrote that down. What that works out to is J alpha Fij alpha inverse partial del x I alpha partial x j. All right. So in just a second, we'll plug this term back in right there. All right. But let's go ahead and also look at what del what del of that guy is. And so to do that, I'm just going to rewrite it. So I'm going to move the numerator to the, I'm going to move the denominator to the numerator with a -1. It's almost always to take derivatives of fractions that way, right? So what I'm going to say is that del of the expression right? So I just rewrote this like that. Yeah.
Is the formula applicable for material derivative only, or
This thing,
Yeah.
this becoming that?
Yeah.
No, this is like linear algebra. You take a class in linear algebra. This is like an identity you learn. The partial derivative of a matrix with respect to the components of the matrix works out to this.
But there should be a trace component there, right?
No, this is right. I think we derived it.
Yeah, we did derive it.
Yeah.
And it wasn't consistent. Check it with the online resources that I have.
Mm-hmm.
They are showing that there should be a trace component there.
That's wrong. The derivative, this is definitely right. If you want to see it again, I'll work it out next time.
Sure.
Okay. But this is definitely right. Okay. So everybody see that, right? These are constants, so there's no variation of them. So like if you're trying to take a derivative of a constant, it's nothing, right? So basically using the product rule, right, I have the variation of the first term, the variation of the first term times the second, plus the variation of the first term times the variation of the second, right? But the variation of the first term is 0. So basically I can just move the del operator there. Now, what I'm going to do is I'm going to replace this guy with I'm going to replace this guy with J alpha phi alpha rho alpha. That just comes from this equation. Right? If I multiply it through by the denominator, then I have J alpha phi alpha rho alpha is equal to the reference. So I'm taking these and I'm replacing with that. Everybody see where that came from? Just using that equation. Okay. Then I'm going to compute the derivative of this thing. The first thing I got to do is take the derivative of the outside, so it's going to put a -1 there, right? So I'll put a -1 there. So I'll put a negative sign out front. And then use the product rule for the inside. Del phi alpha rho alpha plus phi alpha del rho bar alpha Oh, I guess when I took that derivative, I should have also moved down a phi alpha rho bar alpha squared. Right? Well, I took the derivative of the outside. That's minus 1, this term squared. So it's a minus 2, and I put that back here. Right? And then, so obviously one of those cancel. Right? This cancels that. And then ultimately I get minus j alpha get that. Okay, so I'm going to plug that in there. I'm going to plug that in there. So I'll just rewrite del C1 equals the integral in the reference configuration lambda alpha j alpha f alpha ij inverse partial del x I alpha partial big X j alpha plus lambda alpha there, right? So the minus sign got canceled out with that minus sign in the original equation up there. So that's what you get plus there now. All right. So now what? Oh. I'm trying to think about the best way to explain this. I think I'll do it. I'll just write it out and then I'll explain what happened. Should be a summation over alpha here. Okay, so ultimately I want to write all the equations in the current configuration. Okay, so what I did to go from here to here was a push forward operation, right? So, right, remember, little dv is equal to j big dv. So if I want to go the other way, what is it? Big dv, this should have an alpha on it. Oh, it does, yeah. dv 0 alpha, if I want to go the other way, it's 1 over j little dv, dv over j alpha, right? So that when I do a push forward to the current configuration, the j's drop out, right? And then the other thing I did was I converted this derivative from big X to little x. And because little x is a function of big X, right? So basically you can just apply the chain rule, and what you'll see that pops out is an Fij. So the integral over big X is Fij times the integral over, not the integral. The derivative with respect to big X is Fij times the integral with respect to little x.
Yes.
So then the Fij and that Fij inverse cancel.
Yes.
Everybody got that? So I did a push forward to the current configuration, and I converted the derivatives with respect to the current values. Okay? All right. Oh, there should be del. There should be a del there. This is partial del xi alpha, partial xj. No, that's little xj. Remember, little xj is just, they're all in the same place, right? It's only the variations that have alphas on them, and only the reference position vectors that have alphas on them. Okay, anybody have any idea what I might do next? Remember what we talked about, integration by parts? What might I do here? Ultimately, I want to evoke the arbitrariness of that. And I can't, while I can say that the function is arbitrary, I can't, I can't just say that the derivative of the function is arbitrary. So I can't just cancel that whole term. I have to do something here. I need to get this derivative off of that thing in order to invoke the arbitrariness of it. So what would I do? Integration by parts formula, right? So what I'm going to do, again, I think I'll just write it down, and then we'll talk about it. Sum over alpha, integral over b, lambda alpha, this is integral over the boundary of b ds, and that's a little s, minus the integral of b partial lambda alpha partial xj partial x alpha I plus lambda alpha Okay, so basically what I did was I used my integration by parts, right? To shift the derivative onto that term, it generates this thing plus a boundary term. And then I just wrote it out in additional notation. Right? So this is the final equation for the variation of C1 in additional notation. I'll write it, I guess, also in vector notation, we'd have the sum over alpha integral over the boundary, lambda alpha in hat dotted with partial xi alpha minus the gradient with respect to little x Okay, let's just see if it makes sense. Anytime I'm working with tensors, I always just make sure every term has the same order tensor, right? So here we have a unit vector and dotted with a vector that contracts to a scalar times a scalar, so this thing is a scalar, right? We have the gradient of a scalar, that's gonna be a vector, dotted with a vector, gonna be a scalar, right? And then this is a scalar. So every term works out to be a scalar. All right, so again, this is kind of the complete variation of that first constraint, and then later we'll collect the terms, right? So we'll invoke the arbitrariness of del x, right? And we'll collect that term and that term. Well, this term in surface, or these will become boundary conditions essentially because they're surface integrals. These will be we'll collect these terms, the del lambda. And then we'll collect each of these terms. So like 1 over phi alpha, 1 over rho alpha. We'll go to each of those, right? Not going to have enough time to go all the way through the next one, but we'll just say okay, we'll just start by saying this. C2, our second constraint, is integral in the current configuration p of little x and t sum over alpha phi alpha minus 1 dv. Okay, so notice before there was, basically the previous constraint, there was multiple alphas because there were multiple conservations of multiple statements of conservation of mass, right? Here, there's just one equation, this thing, the volume fraction constraint, and we're using a Lagrange multiplier just because I wanted to use a different symbol, because they're different Lagrange multipliers, right? I'm going to use the symbol P. We'll see why later. I chose P when I could have chose anything. We'll see why I chose P. So, but just be clear, this is a Lagrange multiplier, and it's defined in the in the current configuration, right? So this integral is in the current configuration. And I'll just say this, and we'll talk more about it next time, is a little tricky to compute variations of things in the current configuration because phi is also defined in the current configuration, right? Phi alpha is phi alpha little x t, right? So if I need to compute a variation of this thing, well, I need to compute the variation of this field, but this field is a function of another field that also needs to be varied, right? You see what I'm saying? Remember when we compute the variation, it's like, we want to form that star function. So that's like phi alpha plus epsilon del phi alpha. But what goes in here is also varied, right? there's also an x star, so that's x plus epsilon, something like that, right? So there's like a little trick here. So we'll do it next time, but what we'll see is that it's useful to pull it back to the reference configuration, compute the variation in the reference configuration to get the result. All right. So yeah, I don't think we have enough time to go through that now, but we'll get through it next time.
Can you please scroll to the place where you wrote C1 sorry. First answer. Yeah. So that essentially is 0, right? The J alpha minus because of conservation of mass.
This? Yeah. So all your constraint equations need to be in the form C equals to 0, right?
Okay.
So just like before, the second one, right, was this equals 1, right? But we're writing it in a form that it's like this minus 1 equals 0. Right? So your constraint equations need to be in the form, everything on one side of the equation.
Is there a particular reason to make it 0? Is there any particular reason for that?
Oh, you mean in this form?
Yeah.
Yeah, I mean, like how else? I don't know how else to write it, right? Basically, you need to multiply by a Lagrange multiplier that's going to enforce this constraint as 0. So I don't know, like you can't really write an equation in there.
Okay.
Yeah, right.
Is it just to invoke the arbitrariness of the equation?
Yeah, ultimately, right? We want to get everything where it's just like something times a del operator, right? And then we can evoke the arbitrariness and we pull all those things out.
Okay.
Okay.